Hi everyone and welcome to this new video about three-phase power circuits, and we will continue with the unbalanced systems. This is our example number 8 and we will discuss the unbalanced delta Y system in this example. So we have a delta connected source and we have a Y connected load, and it will be unbalanced. It will be clear shortly why is it unbalanced. So let's read first what the situation is. The following data is given about this delta Y system. The phase voltages VA, VB and VC, as shown here, have amplitude of 100 volt each, and the phases are 0 degrees, 120 degrees, and minus 120 degrees. So that's actually the sequence for the phases for this circuit. And we have loads ZA, ZB, and ZC, which are ZA 10 ohms, just resistive. ZB is J8 ohms, so pure inductive, and Z of C is minus J5 ohms, so it is pure capacitive. As you can see, these loads are not equal to each other, for sure not in magnitude, also not in phase, so we have for sure also an unbalanced load, and in total will result in unbalanced system. So what we like to know is the following. Calculate the following: total absorbed complex power by the loads. So what is the total power, what's absorbed by these loads, so 3 of them together, and what is the power factor of the PF of the loads. So we have two questions. First, let's consider actually the circuit itself. Because it is an unbalanced load, we cannot consider some familiar formulas we have for the balanced system. We have considered in example number 1 to number 4. So we have to be very careful and actually apply direct analysis, the mesh current analysis, and the nodal voltage analysis. So depending on the situation, of course, I will use in this example again the mesh analysis. So I will make a mesh. I will make the mesh here on the top one, and then a mesh on the bottom one. So I have two meshes. I will develop the equations for the mesh equations. So, and I will again continue analyzing the mesh currents, and I will use the mesh currents to develop the equations for the values, such that I can determine the complex power for the load. So let me first denote the mesh current. So for the top one, it will be in this direction, so it will be circling like this. In the clockwise direction will be I1, and for the bottom one it will be circling like this, and it will be I2. Okay, that's actually for these mesh. Let me now develop the mesh equations. Okay, for the first one, for the top one, what I can do is I can just start at any point and I make a circle and I end up at the same point. So it depends actually, it doesn't matter where you start, as long as you come back at the same point. So I will start, for example, at point B and make the loop, and for the other one I will start at point A and make the loop and come back again, and I will develop the two equations for the mesh. So what I have is the following: minus VC I have here, and the two impedances ZB and ZC will see I1 as positive, but we'll actually see the I2 in the opposite direction, so we have a minus ZB times I2. So what do I have? It's the following: I have minus VC plus two impedances ZB and ZC, which see I1 in the positive direction, but I2 will be in the positive direction for ZB only, and this will be 0. So this is actually for the first equation. If I now rearrange this such that I have the voltages at the right side of the equation and the current parameters at the left side, and in order I1 and I2, then we have the following: ZB plus Z of C times I1 minus Z of B times I2 will be V of VC. So that's actually for the first equation. Let me write the second equation on the right side. So the second equation I can develop from point A. So I will make minus VB, and then ZA plus ZB will see I2 as a positive current, but I will have for ZB I1, which is in the opposite direction. So what I have is the following: I will have minus V of B plus Z of A plus ZB times I2 minus ZB times I1, which will be 0. Now if I again set the equation such that I have the voltages at the right side and I have the currents in the right order, I1 and I2 with their coefficients. So I will have the following: minus ZB I1 plus ZA plus ZB together times I2 will result in V of B. And that's actually the second equation. So let's substitute the values, what we have given here. So it's 10 ohms for ZA, ZB is J8 ohms, and etc. So for ZC is minus J5 ohms. So what we have is the following. So Z of B will be J8 minus J5 for the first term, I1 minus J8 times I2, and this will be 100 phase minus 120 degrees. What I want is I will simplify this, of course, and I will convert this expression also in the rectangular form, which is actually done many times, so I will leave the details out, so I will move directly to the answer. What we have is here, of course, J3 in effect, so what we have is the J3 I1 minus J8 I2, and this will result in, if you do the math correctly, 100 times minus a half minus J square root of 3 divided by 2. That's actually the answer for the converting the polar form to the rectangular form for this one. Alright, so we have the first equation. This can be of course further simplified, but it's okay for this moment. Let's move on for this one. So that is minus Z of B, which is minus J8 I1 plus I have a 10 plus J8, and this will be times I2, and this will be 100, a phase of 120 degrees. So if I now convert this expression again in a rectangular form, again do the math using this familiar formulas we have discussed also in the other videos about vases and complex numbers, what we have is the 100 times minus a half plus this time J, and then again square root of 3 divided by 2. And this one is of course the same for the left side, that doesn't change, so we will just copy the expression. Okay, what do I see? I see actually the following. I have two equations with two unknowns. So I1 and I2 will be the unknowns, and these are all known, of course. So I can develop a set of equations in, for example, a matrix form. So that's just a choice. You can do also in other ways. So I will develop a matrix equation. So let's first do that. Matrix form. So what do I want? I will actually move to this form A, just a matrix I will develop shortly. And there's a current vector I, which will be equal to this, the A times vector I will be equal to the vector B. So I will have the following situation. And after setting up this, I can calculate I by taking the inverse of matrix A, and then using actually this one, I will write it down. So I have the current vector I will be the inverse of the matrix A times the vector B. So if I do this, if I first develop the matrix A and I develop the vector A, B, and also the determinant afterwards using this expression, the current vector I can determine I1 and I2. So we have the following. So there is a matrix with its own coefficients, so there will be a vector and there will be a solution for the calculations of the vector and the matrix. So what we have is you will take the coefficient of I1, which is J3, and the second one is J8, that's for the first equation. For the second equation is we have a minus J8. So this will be minus J8, and the second term is 10 plus J8. So we have a 10 plus J8, and this one will be A1 and A2, and you get after this expression and this side for the vector B, you will have the values for the voltages, so that will be 100 times this one. Then you have the following, so you have the 100 times minus a half minus j square root of 3 divided by 2. And again, for the second one, 100 times minus a half plus j square root of 3 divided by 2. What I can do already is the following. I can simplify by taking a vector, a scalar outside the vector. So I will, for example, take 50 outside the vector. So I have done 50 outside, so I have the following. This will be 50 times minus 1 minus j square root of 3, and the other one will be minus 1 plus j square root of 3. And this will be, of course, easy reading, also for further calculation will be much easier to handle. So what we can say is about the following. This is A, this one is the matrix A, this one is the vector I, and this one completely was B, and this is of course also B, vector B. So I have actually in total all of them. What I want is of course A inverse. So how can I determine A inverse? So A inverse, let me do that on the right side, maybe on the, just continue here, it's better. So the A inverse, the formula for the 2 by 2 matrix, because it is a 2 by 2 square matrix, I can use this simple formula. A inverse is 1 over the determinant of the A times, now comes the job, what do we place in this new matrix? We swap these elements, so the J3 and the 10 plus J8 will be swapped, so they will, you will replace them, and you will take the opposite sign of this term and that term. That's just a formula, so you will have the following: 10 plus J8 and J3, so that's actually the first action, and the second is you will make the opposite sign of this element and this element. So we have the actually this one. So that's actually the expression for the inverse. Of course, we need to determine the determinant of A. For determinant, I look at this expression. What do I do for determinant? I do this term times this minus the multiplication of these two terms. So I will have the following. Write it down. I will have J3 times 10 plus J8 minus J8 times minus J8. That's actually for this situation. If you do the math here correctly for the determinant, you will have 40 plus J30. So if you do the math correctly, I will also do that maybe step by step. Is J30 minus, just working the parentheses, so just J30 minus 24. J times J is of course plus minus 1. So you have here minus minus minus, so it will be again minus, and we have a J times J will be again minus, so it will be a plus. So we have 8 times 8 is 64, so that will be of course together the real part will be 40 and we have the imaginary part of 30, so that will be 40 plus J30. And if you convert this, for example, in the polar representation, it will be handy, it will be 50 phase 36.9, almost 37. It doesn't have any units at the moment, so it doesn't matter also, because we have now this, so we can say if you place this term here, and you have also this one, then you have the inverse. So we can say the following then, let me write it down, then we have the following: I is equal to A inverse, let me make it better, A inverse times B, which is I is equal to 1 over 50 with a phase of 36.9 degrees times the term we have determined, which is 10 plus J8, and then J8 for the second one, then J8 and J3 times vector B, and I will use this one, so I will have 50 times this vector, so I will have 50 times it's minus 1 minus j square root of 3, again minus 1 plus this time j square root of 3. Okay, what do we do next? Now we can already see some vectors that can be cancelled, because we have 50 here and 50 there, so that will leave of course just 1. And we can multiply this matrix with this vector. So what we have is actually 1 over 1 phase 36.9 as an expression for this one, and I will multiply this matrix with this vector. So how do I do the multiplication? I will do that separately, otherwise it will be too cluttered. So what I want to do is following: 10 plus j8. So I will need to do the following. That's just matrix multiplication, the rules for matrices and vectors. So I will multiply this term with that term plus this term with that term. So I will have 10 plus j8 times minus 1 minus j squared of 3, and then plus j8 times minus 1 plus j squared of 3. That's actually for the first. And the second one is j8, so I will do j8 times the first one, and then plus j3 times the second one. Okay, so I have the following: minus 1 minus j squared of 3 plus j3 times minus 1 plus j squared of 3. Now, if you now calculate this, that's actually the next step, that we have to again calculate these two. So what we have, you can do that actually by ourselves, it's pretty easy. So what we have is the following in total. I will just leave the results here, which is minus 10 minus j, and in parentheses I have 10 square root of 3 plus 16. That's for the first one, so this is 16. The second one will be 5 times the square root of 3 minus j11. And this will be placed in the new vector. So this matrix times this vector will produce a new vector with the first element here, the first row, and the second row will be this one. So if I a little bit zoom out, what do I have? As the following: I have I, vector I, will be 1 over 1 phase 36.9 degrees, because this 50 and this 50 made a 1 here, so I will leave that. And I have a vector, new vector, which is minus 10 minus j, and then 10 square root of 3. I can see it is not enough. Let me first write it down. Plus 16. That will be for the first row, and for the second row, this will be 5 times the square root of 3 minus j11. Okay, what I want to do now is I will transform this rectangular expressions for the first row and the second row of this vector to a polar representation, because the multiplication afterwards will be easier. So I have the following, and I will also use 1 over the phase will be minus, of course, and I will have 1 over 1 will be, of course, the magnitude. So what I have is the following: for the magnitude I have the 1 phase minus 36.9 degrees. It's just this term here represented in a different form, and I will transform this in a polar representation, and do this also. So what do I have is the following: I have 34.8 phase will be minus 106.7 degrees, and the other one will be exactly 14, and the phase will be minus 51.8 degrees. If you now calculate this out, so this term times this, and then this term again times the second row, I will have the following expression. So that will leave us with this one: 34.8 phase will be minus 143.6 degrees, and the other one will be 14 with a phase of minus 88.7. And this means actually the following: since the vector I has the elements I1 and I2, which are the mesh currents, I can say the following. Then I1 is the first row, which means 34.8 phase minus 143.6 degrees in amperes, and I2 will be 14 phase of minus 88.7 degrees. And I have now both of the mesh currents. And if I know the mesh currents, I can just continue with the analysis, because all of the other required values, load currents and other required values, depends actually on the I1 and I2, which I have now developed. So what I want is I will move on to the total absorbed complex power. So let's, and what do I know for the complex power? I can use several formulas. What I need is the current and the impedance, or I need the current and the voltage, or I can use the voltage and the impedance. So it depends actually on the situation. What I want is, because I know the currents, I can develop actually the formula for the apparent power using the current and the impedances, because I know the impedances and I also know the currents. Because if you look, the I2, for example, is circling like this in this bottom loop. It will be, of course, equal to the minus of the IZ of A. So it is easy to say IZ of A is minus I2. That's actually the situation. I will also do that for the other ones. So I will have the I1, which is actually in this direction, flowing this direction, will be exactly IZ of C. But IZ of B will be I2, which is in the direction of the IZ of B, minus, of course, because it's circling around like this, and coming back will be minus I1. So it will be I2 minus I1 for IZ of B. So if I now write down the load currents, so first load currents, I will do that here. So the load currents, so let me do that also. So IZ of A for the first one will be minus I2, IZ of B will be I2 minus I1, and IZ of C will be I1. Now I have all of those values because I already calculated here. These are the values. So if I now substitute all those values for I1 and I2 for this mesh currents here, I will have minus 14 phase minus 88.7 degrees. And I can now use this minus as a minus 180 degrees, just a minus 180 degrees phase shift, and incorporate it here. I can have an expression with a plus magnitude. It will be 14 with a phase of 91.3. So I will add 180 degrees here. And this is actually for the first load current. The second one will be 14 phase minus 88.7 degrees minus 34.8 phase minus 143 degrees, 40.6 degrees. And this will result, if you do again the math and combine the real parts and the imaginary parts in the rectangular expression, you will have as an end result 29.1 phase, 12.2 degrees in amperes. And the last one is I1. Just copy what we have for ICZ, which is I1, and what this is 34.8 phase minus 143.6 degrees, and it's actually for the last one. Now I can use the formulas for the total power. So let's move on. So this actually for the question A was total absorbed complex power by the loads. So I know as of the loads, will be S due to Z of A plus S due to Z of B plus S due to Z of C. So I can now calculate each of the complex powers due to each load, and I can add them up and I will have the value. So what is now the expression for the S Z of A, which is 1 over 2, so half, times its peak value of the voltage, or you can do it in a different way, because we know already the load current. We can use the peak value of the load current, so I can do the following: IZ of A peak value squared times the impedance itself. So I can use this formula. It is much easier to use this formula. Why? Because I already know the current. I also know its impedance. So it is better to move on with this formula, which is 0.5 times, the amplitude is 14, just take the 14 squared, times it, and this was 10 with the phase of 0 degrees. So this is still a vector. This is still a vector. So this one is just the amplitude, and this is still a vector. So I have this one. If I now calculate this, I will have, for the first one, it will be 980 phase 0 degrees with a volt ampere. So this is actually for the first one. For the second one, for ZB, again the same procedure. 0.5 times the IZ of B, again the amplitude squared times Z of B, which is a half times IZ of B, which is shown here, the amplitude is 29.1 squared, and ZB was just inductive, J8 will be 8 phase 90 degrees. So if I convert this, of course, in the polar representation, I will have, if you do the math here correctly, just multiply the magnitudes and add the phases. What you have is 3,387, and the phase will be 90 degrees. And again in volt amperes. Okay, that's for the second one. For the last one, SZ of C will be a half times the amplitude of the load current of ZC, squared times Z of C will be a half times the current will be 34.8 squared times, it was minus J5 for the Z of C, will be 5 phase 90 degrees. So again, you do math correctly, you will have 3028 in phase minus 90 degrees in volt amperes. So I have now all of the required values to calculate the apparent power here for the load. So I have done the following, and it's almost done. So S load will be 980 phase 0 degrees plus 3,387 phase 90 degrees, pure inductive, and then plus 3,028 phase minus 90 degrees. Again, you convert this form into the rectangular expression, add the real and the imaginary part. This time is very easy because this is pure real part, this is a pure imaginary part in the positive direction, this is a pure imaginary part in the negative y direction. So what do we have is the following. You will have S load will be 980 plus J 3,387 minus J 3028. So if you now again simplify this, because we have two imaginary parts, so you can simplify this and make it one imaginary part, will be 980 J 360. If I now convert this, because this is just the total apparent power already, we have the expression in the rectangular form. If I now move to the polar representation, will be 980 squared plus 360 squared, and I will take the arctangent of the ratio imaginary divided by the real part, which is a standard formula we already know, which is here given as 1044 phase of 20.2. Very close to that. It will be volts amperes. Now the second, this is actually for question A. For second question, for the power factor, what I need is of course this expression which shows me the phase. So the phase here, the power factor PF is equal to the cosine of the phase for the apparent power, total apparent power. That is in this case positive, and because it is a positive phase, it means it's actually lagging. So I have to make this also clear, otherwise it is not correctly defined. So I have the cosine of 20.2 degrees lagging, and if you calculate this out, it will be 0.94 lagging. And that's actually for this example. We have now the total observed power by the loads and the power factor of the loads, and that's actually for this example in total. So again, as we did in the previous videos, we used different formulas to calculate the load apparent power, so the load complex power. It depends actually on the situation. If you prefer to use the voltage and the current, then you have of course required value here is of course also the voltage across each load. I also need to do additional work for that, so I will skip that and use the current I already know from this analysis, because it's much easier to do that, and I will use the impedance which I already given in the analysis in the question. Alright, this was for example number 8 about unbalanced system. We have the unbalanced examples, actually all of them now done for different configurations, and it was the last one for delta Y system. And if you have any questions or comments, please let me know. I will try to answer them as soon as possible. And don't forget to share and like, and I see you next time, and take care.